Good morning. My name is Chandraneil with my team Saxena, Bhumika, Pawan and Nishant to tell you a brief info about binary counters. But first, what is a counter? A counter is a circuit that produces a numeric count each time a input clock cycle makes an active transition. Here there is a counter in which there is a clock. When there is a active transition in the clock, the count increases one by one. There are some optional inputs like reset the value to 0, start with an initial point, load the initial point, select the direction up or down, etc. Counters are very widely used components in digital circuits. Their counters are manufactured as a separate integrated circuits and are also used as a part of larger integrated circuits. Counters are differentiated by its different characteristics. Characteristics like modulus. Modulus gives the length of the sequence. Differ by number of basic characteristics it has, like modulus. Modulus gives the length of the sequence. Coding gives the sequence count. Direction, it tells us about it is incrementing or decrementing, that is up or down direction. Resetable is to reset the count to 0. Load is loading a value into the counter. Now we will talk about counters applications. It is used in system clocks, timer, stopwatches, alarms, cycle control, system control, sequence control, etc. Till now we have seen that counter is a circuit which just counts. So the number at which it starts its initial count and the number at which it ends its count depends upon its design. This counter consists of two JK flip-flops. Now the most important thing is that the clock here is not same for both flip-flops. Here the clock is negatively edged, and here the output of the first JK flip-flop is acting as a clock for the second flip-flop. In this diagram, as the clock goes up, there is no change. When the clock goes down, the QA goes up to 1. So here it is 0 and here now the QA becomes 1. And when the clock again goes down, the QA becomes 0 again, and when the clock again goes down, it becomes 1. So the cycle goes on. Now QB is depending upon QA's output. So when QA drops down to 0, QB becomes 1. So till now it was 0, now it will become 1, and it will drop down to 0 when the QA drop down to 0. So this is this output of both QA and QB. You can see that the time taken for one clock cycle is Tc, and the time taken for one cycle of QA is Ta, and of QB is Tb. The relation between these three is Tb, which is this, is twice of Ta and 4 times of Tc, as you can see this in the picture. As a frequency is inversely proportional to time, so Fb is twice of Fa and 4 times of Fc. Till now I haven't told you about how counter gets incremented and how counter gives a number. So from this table I will tell you all about it. First, we are considering the clock cycles 0, 1, 2, 3 and given in the clocks, and QA gets incremented to 1 at clock cycle 1 and 3. So at 1 and 3, QA gets incremented to 1 and other places is 0. And QB gets incremented at 2 and 3. So QB will become 0 at 0 and 1, and 2 and 3 it will get incremented. So this is the binary number for 0. So this 0 is stored in counter at this stage, and at this stage the number stored is 1, and at this stage the number stored is 2, and at this stage the number stored is 3. So I haven't taken the other cases because after getting 3, the a counter again counts 0 because the conditions after this keeps on repeating. The counter counts 0, 1, 2 and 3. So it is a 2-bit counter.
So, as you all know, my friend Basa explained about the counter. Now, I am going to explain the different types of counter. So, there are two types of counter. Here you can see that there's a asynchronous counter, which is also a ripple counter, and a synchronous counter. So, here I have drawn the diagrams of both the counters. Now, I am going to explain about you about the asynchronous counter. So, here in the asynchronous counter, there are two inputs coming. First is the counter and second is the clock. So here what happens, the clock goes into the first flip flop, then the output of the first flip flop goes into the second flip flop, and it goes on into the other flip flop. So here we can say that the both the all the that flip flops are dependent on the output of the first flip flop, which is not so good. So here you can see that it is a counter which is going on in the final flip flop, and it's the asynchronous counter. Now I am going to explain you about the synchronous counter. So here you can see the diagram. Here is the AND gate, and here you can see that there are two inputs coming. One is a counter and second is a clock. So here you can see that the counter is going into the first flip flop, whereas in the asynchronous counter you can see the counter is going into the last flip flop. And here you can see that the clock is available to all the flip flops simultaneously, which was not there in the asynchronous counter. And here you can see that the other flip flops are not dependent on the first flip flop, which was there in the asynchronous counter. Is that the flip flops are not connected simultaneously, whereas in the synchronous counter the flip flops are connected simultaneously. You can see here. As the number of states increases, the circuit is simple, whereas the circuit becomes complex as the state is increasing. Here we can see that the speed is slow and truth.
Hello everyone, today I'll be telling you about up counter and down counter. It will have variable values as input 0 and 1. C is counter starting bit, R is counter reset bit, PV is preset value of counter, CV is present value of counter, and Q is output bit. Now when the counter trigger bit C passes power, then the current value CV is incremented by 1 when the current value is equal to the preset value PV, then the counter output bit Q is turned on and the instruction passes power. Now I'll be telling you about down counter.
So here we want toggling, and for toggling we have to make JA, JB, JC equals to 1 and as well as KA, KB, KC is equals to 1. And I have given common inputs to all the inputs of the flip-flop which is logic 1. It means it is high, and it is high, so definitely we have toggling. And now next point comes the symbol. It shows a negative edge triggering. This bubble means negative and this arrow means H. And these QA, QB, QC are three counter outputs in which QA is least significant bit and QC is most significant bit. Now we have to consider analyze time. So now we will consider this timing diagram. So now we will consider this timing diagram, and in this circuit, in this diagram, the external clock is given to the output number QA, and so here we have QA, and initially here we have 0. We will analyze this timing diagram, and here the external clock is given to the output number QA, and which is the next state, and which is equal to Qn ka complement. So here this state will be 1 because initially it was 0, and it will remain 1 till the next falling edge. And now another interesting point comes. For this QB, we don't have to consider this clock or this clock. The job of this clock has been done for QA. Now, if you see in this diagram, QA is going to the flip-flop output of flip-flop B. So now QA will act as the clock for flip-flop B, and we will consider these falling edges. So toggling in B will occur at these falling edges. Now we comes to our last output C. Here again we don't have to see that external clock QA, but we have to consider this QB. So now we comes to our last output QC, and here also we'll not consider that clock or QA. We'll consider QB because here it will act as clock for QC. So toggling in QC will occur at these following edges. So in this way we can plot QA, QB and QC. So actually counting depending upon these waveforms that we have just obtained. Now I will make a simple table, and in this table initially we have the initial condition when the clock is just applied, then first falling edge, second falling edge up to this. So now you can see we start counting from 0 and ends up at 7, and it goes again to 0, and if this happens we just passes the clock pulse before 0, and here we can see maximum number of states are 8. So 2 raised to the power n is equals to 2 raised to the power 3 equals to 8, where n is the number of flip-flops, and so in this way you can get the maximum number of states. And if you want to get the maximum possible count, so the formula for this is 2 raised to the power n minus 1, which is equals to 7. And so here we saw how 3-bit asynchronous counter works. It is up counter. Up counter means every time clock pulse is passing you or your value, it is getting high. So it is what we have to do actually with up counter, and similarly with down counter we will consider the rising edges instead of falling edges, and we'll consider rising edges, and in up or down counter that is a combination of both we use rising edge and falling edge both. So thanks.
Hello everyone, we are explaining the logic of binary counter here. And we are also try to explain how the binary counter is designed using T flip-flops. First, we need to understand how the binary counter works. So, first, to design an n-bit binary counter, we need n flip-flop, and these n flip-flop can generate numbers from 0 to 2 to power n minus 1. For example, if we have 3-bit binary counter, then it generates 0 to 7. Now we are trying to design 3-bit binary counter with 3 T flip-flop. First of all, we look at the table of T flip-flop, excitation table of T flip-flop, and we have input Q, and we want if we have input QT and we want QT plus 1 next in the next round, next pulse. So if we have 0, then we want 0 in the next pulse, so we give T 0 to T. If we change from 0 to 1, we give 1. If we change from 1 to 0, we also give 1. Here the output, here the state is changing. Here the state Q is changing from 0 to 1 or 1 to 0. Then we need to give T equal to 1. Okay. So we are designing 3-bit binary counter, so it can count from 0 to 7. It has 3 bits, 0, 1, 2, 0. A is the most significant bit and C is the least significant bit. For example, in the first round, it changes from 0 to 0, 0, 0 to 0, 0, 1, and 0, 0. Then again it changes from 0, 0, 1 to 0, 1, 0. Then and again it subsequently changes to 0, 1, 0 to 0, 1, 1, and that process continues until it changes to 0, 0, 1. So it works in a cycle. So this is the excitation table for 3-bit binary counter. Suppose we have first 0 0 0 state, means all three values are 0. We have 0 L. So we want to change it from 0 0 1. So if we want to change in the C bit, then we have to give in the third C of T flip flop, we have to give 1, another 0. T flip, remember T flip flop is used for changing the value, toggling the value actually. So if we want to change from 0 0 1 to 0 1 0, so here you can notice that 0 changes from 1 and 1 changes from 0. So we have to give both TB and TC both 1. And if we want to go to next stage from 0 1 0 to 0 1 1, here you can notice that 0 and 1 are same, only this 0 changes from this 0 changes from to this one. So we only need to change T flip, we only need to give 1 to the T flip, C flip, C T of C. Now if we want to change from 1 0 0 to 1 0 1, so you can also notice that these values are same, but only value this is changing from 0 to 1. So we need to give 0 0 1. Ti and tv are 0 because these values are not changing. The value which is changing is c, so we need to give in the third flip flop 1 given. As this is continued till we reach 1 1 1, and again if we want to reach 0 0 0, here you can notice that all three bits are changing, so we need to give 1 in all flip flops. Okay, so in T flip flop, if inputs and inputs are 0, then next output is same as the previous one, as you can see that. We now write function for T flip flop. For example, if we have to need minimized function for TA, TB and TC. So let's try to write function from this table. Okay. So here you can see that TA is 1 only when this is 1 and these two values we have 1. So here we can write function for TA. Here this is 0 1 1, so it is A bar B C, and you can see that here it is 1 1 1 A B C. Okay, so if we can take out A B C, then it becomes A plus A bar, and you can use Boolean law to prove that this becomes BC. So we can get a function from BC, function of TA from here. Okay, now let's come to the function of TV. For TV we need to see that when TV is going 1, so you can either design using K-map, or you can just observe that when the value of C is 0, the value of TV is 0. When the value of C is 1, the value of TV is 1. When the value of C is 0 again, then TV is 0. When C is 1, you can continuously see that these two lines are same. So we can write TV equal to C. Okay, now you can see that TC is never depending on any kind of output. It always remains 1. So it is 1. Okay, now we have all three functions. We are trying to design the flip flop of these functions. Okay, thank you. Here it is the flip flop of 3-bit count. Here it is the system of 3-bit counter. You can see that TC is always 1. Okay, so now what is TV? Our TV is here. We got TV equal to C. So we just need to connect wires of C from C to TV. Okay, now what is TA is B into C. So we need an AND. First we take the C cable and C wire, and we take the wire of B. connect them using AND. So these TA has input BC, so you can get input TA from BC, and TB has C, and TC has 1. Being bun, and you can see that we get output from A, B and C. Okay, thank you. Content for, okay, we got this content from nesoacademy.com, and we also take the help of our teacher. Okay, we are thanking for the Neso Academy and our teachers for supporting us in completing this video. We are also enlisting the link of Neso Academy in the description. You can check the link of Neso Academy playlist in the description.